Good morning. My name is Osvaldo Bascour. I'm a principal and consultant fellow with OSB Digital and SIC Advanced Analytics. This paper is a joint paper with Freddy Redamal, which is the gerente de automatización y tecnología de Minera Lumina Copper Chile. El título es Integrated Rock Processing Strategies in the Digital Age. The reason that we gave this title to our presentation is because we are dealing with very, very low or grades, which changes the strategy on how we need to manage the plant. In addition, we are working in very high remote locations. So today, using the cloud is a must to be able to activate the use of the data that is collected and sometimes used improperly when you don't have the right knowledge to process it in real time. We have to teach the computer to really transform that data into information, to develop models, and to present it to operation for their better decision making. You got the summary here. The most important part that I wanted to touch is basically that we have very hard winters and we don't have a large latitude for variation in the processing conditions. As such, they require a synchronized operation with one version of the truth. And this version of the truth is based upon dynamic models, which enables to help and generate the mass balances and all the energy and levels and inventories which are required to maintain stable operation. So we're going to talk a little bit about the digital age transformation secrets, the fourth step to maximize metal production, the dynamic decision support using hybrid process models and predictive analytics, and some live examples of what companies are doing. Today, we need to reduce the variances between the production plan and operational result. We have to cleanse the data and add the missing information for improved decision support. Grinding DynaMill with viscosity model and flotation with air Holdup provide adds the missing information to the set of data collected in the operations. And this has to be done by the people at the plant. It doesn't work if we let other people doing it. So that's why we require a special implementation strategy. We have to choose the right KPIs for the digital age. We have the technology to transform the data into real information. So these are the KPIs that we should be using. Effective communication and improved decision support is a must because now, since everything is in the cloud, everybody can access it, but especially because we have the right information, everybody can contribute. And we have to avoid the hidden production losses and equipment failures in real time. This is a must and basically sometimes ignored, but this is the most important part that goes through when you start building a digital twin plant for your operation. It allows you to synchronize everything together. And of course, you can innovate your operational process using the cloud, this remote work. Now with the COVID, this has been a blessing because we can contribute irrespective of where we are. This digital disruption promotes dynamic mining, mill performance management. People is the most important. That's what I'm saying. This cannot be done by someone externally. It has to be done by the people. And they change their business culture and processes. And this is what takes time and it requires a special treatment. The new technologies should be embedded into the system so it becomes transparent to the user. So basically today what we see is that we got all these silos with this breakdown between management and operation. Management requires transactional type information, so we need to use the operation with their event frames to transform the data into transactional information in real time. That's a must. And engineering can use it and put the models, and they are the guy in charge of developing and maintaining the models. That's it. They are the ones that understand the process. Maintenance, on the other side, they know the equipment and they can do that. And mine, of course, they can do the mine the way that they understand it. So what we got today, the critical pain points that we see in the production processes are there is a drastic energy and water cost with lower grade ores. There are potential hidden costs that are due to the trouble times and the downtimes that these plants operate at because they are very, very hard ores and it's very difficult. Losses of copper through the tailing thickeners. This is due to the bad liberation or the bad flotation on the roughers. And this is what we're going to take care today and try to share the light on how we have been able to do and transform that. We have a lot of disturbances due to the mineral or viscosity. The transportation of the pulp through the plant has to be flawless. And this is something that sometimes is ignored because we cannot really measure it. So we need to use the most advanced technologies to predict how the viscosity is affecting the whole production line. And of course, when you start minimizing energy, start uh, augmenting the water recovery, you are more sustainable. You are doing the best with the ore that you are receiving from the mine. So dynamic water recovery model is something very, very important in today's targets. We got multiple sets of data, raw data that needs to be transformed. Mining data sometimes is unavailable, so we need to capture that in real time. Not current or misses information is the typical norm. We need to organize that in what we call the digital plant model. There are a multitude of spreadsheets that has to be reduced to one version of the truth. And communication between management and operation needs to be maximized. So the relationship between reporting or analysis has to be able to be understood by management so they can collaborate as well. This is not something that is delegated to someone else's. Everybody has to be in the same playground to do the optimization and maximization of copper in these plants. Operational results sometimes don't match business objective, and this is because the people that are doing the planning are not using the real data, I mean the real plant data, and that's really sad. One of the key things is that grinding is not only for liberation, it's also for maintaining the right equipment correctly, the cyclones, the flotation cells, the pumping, and also the most important is the water recovery. The bad size distribution that we can have in a ball mill circuit repercute throughout the plant. Once we get a bad particle size distribution outside the region in which we can do the flotation, do the water separation, and get the concentrate that we need, we are losing tremendous amount of money. So we need to monitor the production loss and failure in real time. We have to predict the production using and analyze using tools like Power BI. We need to identify the targets or the tendencies in which the data has to behave so we can identify what we call the constraints of the plant. This is really the 4 steps that we are using to implement the analytical models using hybrid models with the specific constraint and the variables to optimize your process. This KPI setup is done in real time, respecting the constraints which are identified in the prior step. The third is to really transform that data into information to develop predictive analytic models so we can be ahead of time and not going back and solving problems. We need to share this analysis and reporting tools to management so they get access and they understand in the journal what is going on. And here we identify the best uh, process conditions through the analysis of the historical data. And such, we get better report, we engage stockholders, we are using machine learning process, and we share this report with people locally and also people that are helping to optimize the value change management. We do that by connecting to the historians. In this case, it's the OCSoft or Aviva now by system, which connect to a repository that manage the collection of data from many sources And we can see these sources in the analysis tool, which is called SIG Workbench, which is really the human interface to the data and to information, to the events and to the external metadata that is required to model the plant. Then we have the organizer where the engineers and whoever wants to do the analysis are presenting these to the team, to the core team, so they are understanding how the analysis, how the plant is affecting the bottom line. And if you want to do and involve data scientists, you can also use Python, which is included in the data lab environment for further analysis if you require. So the opportunities to increase metal production are very well known. This is a paper that we presented the process grinding control many years ago, in which we try to maximize the throughput through the mill while the recovery sometimes is suffering. But we see is that there are constraints like the mill overflow or the cyclone roping. And also, we know that the real cut point is the business cut point. So it's a compromise on how much copper we are producing in relationship to the constraint. And if we got that target in real time, we can really move towards the constraint without violating and reducing the variability of your cut point to the maximum. So that reduces as well the changes in rheology that affects the whole plant. So we modeled that through a digital twin concentrator model where we put objects, which are the crushing, grinding, flotation, thickening, and tailing. And we, first of all, we manage the whole energy that we are using in each of these steps. We try to maintain the flow as much fast as we can. So that's the maximum throughput that is represented through the combination and the synchronization of all the steps in the plant. And then, of course, we are using water or recovering water in certain areas, and that has to be managed so we get the maximum water recovery while we are maintaining the maximum copper production and the waste that with the minimum copper losses. The key thing of the digital twin is that we have the metal copper production in real time as a metric that we are calculating every time that we are moving in time according to the mineral type, the mine planning, the cutoff grade of the mine. That's the grade that is very, very important because if the grade drops, of course, the copper is going to drop. So the mine has to be producing a stable input to the plant. And this is where we fail sometimes. Sometimes we see that the grades become very low, or there is a shortage of mine production, and this is shown in many places. And then, of course, the recovery in the flotation is very important, and also the recovery. If you want to do this for water, is the same. The water becomes extremely affected by the tonnage, of course, the grade, and the way that the rheology of the plant has been doing. This is the rheology of the operation, the rheology, the water, the hydrodynamics on how we are moving the particles, bubbles, and water through the plant. And of course, the availability is very much included in the way that the recovery is calculated and, and so on in real time, because this is too much information for someone to do it. The computer is trained to understand this problem. Here we see an example in which we have the copper recovery and we have the copper production, and you can see by analyzing the data at different throughputs on how we find that there is an optimal P80, let's call it, but also is important is the form of the size distribution we calculate at the same time. And we can see that this particle size is directly related because this is at the same time, so we can do many analyses here in this beautiful SIG environment, which allow us to analyze all these multiple variables. And we see here the maximum particle density that we need to feed the cyclone. We can see the densities that we have in the mills. All those are calculated with the soft sensor, which are included in the digital twin plant model. This is an example where we tailor the solution. We are calculating the size distribution entering the grinding. We're calculating the size distribution coming out of the grinding circuit, and we are seeing how this is affecting the net metal copper production in real time, the effect on how we are managing the viscosity in the plant by having the right densities throughout the plant and not having large viscosities, which really really you get bad grinding, and of course you can have overflow of the mills or roping in the cyclones. And this is done in concert with the model that has been generated over the years, which is called DynaMill. We can see here the effect of the nonlinearities that happen both in grinding of different particles and also the rheology, which is affected by the size distribution and the effect of when we get into a very dense pulp. And of course, the changes that we might have in density of the miller are also included, so we can identify what the constraints really are in real time. This is the flotation model. The flotation model is a zero order process in which we got a tank with agitation, and we are catching the particles through the bubbles that are being generated by some form, and then these are moved up into a column, and the column we have to know that this is the hair holdup at the bottom here and then at the top, and we are doing this management of air that that provides the best recovery possible at all time by doing that in real time. So you can see the froth is changing because as you change your tailings, you can change everything in your cell. So you have to be very careful on how you manipulate your tailing for the bank. And as such, we manipulate that correctly by identifying what is the best profile that we can get for all these variables that are here. This is a lot of information that the only way that can be understood is by applying the latest algorithm that we have developed, and they are available for deep analysis. Here we can see the net metal recovery, production, and we have the P80, and then we understand all the variables which are associated and the effect that these are doing, what are the ones that are constrained, the one that we can manipulate. So we have a good X-ray of the plant, both from the grinding perspective and the integrated grinding flotation. We also have the thickening. I don't have the time to present that today, but basically we see that if we improve this grinding, the water recovery also improve. And the problem is to solve this problem as you are going. Are we on target or we are getting out of target? Identifying the root causes and developing the models is part of engineering. So they are the ones that are using the tools, coming up with a solution, and then management needs to decide what are the alternative, where we need to go, what are the decisions. There are so many important things that needs to be done as we are moving through time, month, and so on, because the ores are changing drastically. It's like receiving a different ore every day. So this is where we need to identify the capital investments to really maintain the plant and innovate with the data that we have. So the data is not only using for reporting, for build the model, it's also by defining what are the incentives to do things which sometimes might take some time. So that's what we call the left brain, where we try to go with the plant, and the other one, which is really challenging the plan. Why don't we do this? Why don't we do that? Can we do that? So this enables you to do a lot more analysis, which is required in today's way of running the plant. And of course, people, new technology, and business play this triangle here, where we have to decide uh, faster with the best information. We have to communicate this correctly. So the system that we are suggesting enables you to do that by getting everybody to work together. And the new technology is available, so we need to train the people in this. They need to become the skills has to be changed. So that's why we spend time with the engineers, which in 2 months are really up and running better than anybody because they have the problem and they understand the problem better than anybody. That's called subject matter experts that are retrained to use this new tool. And then we get new business processes where we can have optimization of the yields, optimization of the cost, and equipment failures in real time. So we get maintenance, engineering, operations, and management working together. So we have many examples. The most advanced one is ArcelorMittal in Canada, where they got two open pit mine, one pellet plant, and the railway, and of course the grinding plants, which they have 8 lines of ACK milling and separation. This By implementing this digital twin model for the whole complex, they got 120 million additional revenue in 2015, and this is now being revised, and now they have a center of competence where they have really improving from where they got started a few years ago. Anglo American is pretty much also a multi-site environment where their target was 15% reduction of energy. So they come up with many projects, and the key thing was to really connect with the local energy provider. Barrick had the same problem, very large variation in the mine. The gold recovery needed to be understood much better, so we implemented the size distribution model for the grinding and for the cyanization and the recovery of the gold, which is trapped into the solids by improving the operating parameters, of course. Alumina copper, where we're using now SICK, in addition to the other tools that we're using before, that are really embedded into the use of the real-time series information collected by the PI system. So active stabilization of the plant using the predictive models to avoid the constraints and identify the losses when those constraints are being violated. And that is really how people changes, is when you are following the money on how you're operating the plant. So we are decreasing the bottlenecks, and this is very important to identify where are the constraints and how the bottlenecks are changing depending on the type of ore that you are producing. Because the rheology changes according to the size distribution, mineral type, and so on. So it's a never ending story there. So the key thing is to develop this digital twin plan to be able to hand that into the people to identify the losses. Once the losses are discovered, we tailor the model, we do the predictive model generation, we deploy that in real time, and management and coaching after deployment support is available, and is available through a cloud solution. Because really, this can happen and people are moving around. They might be at the mine, they might be in the capital, they might be where they're living, uh, and so on. So it doesn't matter where you are today, this happens anywhere. And then we optimize the operation fluidity and rentability. If you have any question, you can contact me at OSB Digital LCC, and I'd be glad to answer additional questions. Thank you very much.